Let's take a look at what is inside a digital image. Most of you probably already know, but let's just dig a bit into that topic. First of all, we can take an image like the drone or the logo for the Wild Drone project. And if we try to zoom in on this, we can actually see that this image consists of a lot of small elements. These are called pixels or picture elements. And each of these elements have three color values associated with it, which describe the color that is present over here. Let me see if I can find a good region here where we have some different colors. We have a quite dark region over here. If I click in that part, I can see some values over here that denote the amount of red, green, and blue light that is used to describe the color down here. And if I take a brighter patch up here and then click, you can see that the values will be updated to some values that are much higher. So far so good. So an image consists of a lot of these pixel elements, and if we can utilize the values in these pixels elements, we can actually do calculations with them and so on. So let's go back to the slides a bit. The basis for using free values for representing colors comes from the fact that our eyes are sensitive to three different kinds of light: blue, red, and green. And by adding different amounts of blue, red, and green light together, we can actually generate colors that match more or less all colors we're able to see with our eyes. So for instance, if you have the blue light and you mix that with green, you get this cyan color. And if you take the blue light and mix with red, you get this magenta color over here. We can also formalize this a bit by introducing this color cube, or this red, green, and blue color cube, which is a way of visualizing 3D space where each point in the 3D space gets an associated color based on the amount of red, green, and blue light for that element. So if we look at the arrows down here, it indicates where we have less blue light and where we have the maximum amount of blue light. So we have 0 blue light and 100% blue light here, and similar for the red and for the green color channels. So if you look at the corner down here, we have 0% green, 0 red, but we have the full blue color. So it's a rather dark blue color in the location here. And if we increase the amount of green light, we go up and get closer to this cyan color. And for instance, the color value in here is described with these elements: 1/5 of the maximum amount of red light that can be available, 3/5 of the amount of green light, and 4/5 of the amount of blue light, which gives this bluish color. So this is one way of representing colors, by having these three values of the red, green, and blue color components. A different approach that sometimes can be helpful to know is to use the HSL, the hue, saturation, and lightness color space, which has again 3 components, but they have a much different meaning than the red, green, and blue color channels we talked about before. The hue describes the chroma, or the color of the object we are looking at, from yellow to red to blue to green and so on. The lightness is if it's a very dark color or a bright color or something in between. And finally, we have the saturation, which goes from 0, which matches a completely gray color, out to a very bright color or saturated color. So let's take a look at how we can actually look at these different color values. So in the demonstration here, I have the option of changing the amount of red, green, and blue light, and their combination will then be shown down here. So if we start off by having full red, which is 255, 0 green, and again full blue, we get this magenta color, and we can actually start experimenting with, okay, half blue, a half green, and full red. It gives us this pale red color and so on. So by choosing proper values of these elements, we can represent more or less all colors we're able to perceive. But they can be a bit hard to actually find the right colors to describe things with. Usually we have a camera that takes care of that part, but if we want to choose the colors ourselves, that can sometimes be a bit difficult. The HSL, hue, saturation, and lightness color space is a bit different in that matter, because if I want to select different families of red, I can select the hue to be red by putting it here on 0. And then I can actually choose different kinds of saturation of the red color, and also I can vary the lightness here. So I have different options for this. I can also change the hue, so if I want to do the same thing with a green image, a green color, I can again vary it using the sliders up here. And finally, yeah, I can select all the possible values here. The final color space I would like to introduce you to is the CLAB, which is again a combination of different 3 different components. We have the amount of light, or the luminosity, on this scale here, and then we have a balance that goes from blue to some kind of red. If we limit the luminosity a bit, we can also see that it actually goes from green to some kind of red. And similar for the B component, it goes from blue to a dark yellow or brown, but if we increase the amount of light, we can actually see it goes from a kind of blue to a kind of yellow. And these are different values we can use to describe a color. For some applications, it might be beneficial to use a different color space than the RGB that we usually use. All right, let's go back to the slides. One example for using color calculations directly in images is to identify things based on their color in an image. In this case, I have a sample of an image from a pumpkin field, and I have taken a few of the pumpkins and actually annotated them by drawing some red markers or some red pixels on top of that. And these annotations mean that I would like to sample or look at the original image in the same location and actually extract the pixel values of these locations. When I do that, I can generate a plot like this, where I have the blue color channel on one axis, on the primary axis, and the green color channel, or the green color value, on the secondary axis. And here we can see how the color values are distributed. Actually, this actually takes place in 3D, where we have red as the last color channel, but let that be for now. If we then make an calculate the average of these color values, we can get an average color value in here, and we can also look at the arrangement of these points around the mean value here, and describe that using a covariance matrix. This generates an ellipse that tells us where these color values are within this color space. When we know these two elements, we can actually calculate the distance from the center of this set of annotated pixels out to an arbitrary color value from, for instance, input image. And we can use that to take all pixels in this original image and then calculate the color distance to this set of annotated pixels, which generates the image over here. And the benefit of the image over here is that now we have a grayscale image, where objects that have the same color as the ones we annotated earlier will appear very dark. They are almost black in the case over here, whereas all different elements, whether they are wheat plants or soil or whatever, will have a much brighter value here, and we can actually utilize this to segment the image so we can see, okay, where are objects with that specific color we are searching for. So this is one example of how we can actually utilize color values to do calculations inside images. So I hope it made sense what I introduced you to here, and a digital image is just a bunch of these pixel elements that have these three values that describe the color. Good. Have a nice day.